Okay, I'll keep it brief. Moving on from characterization and detection of planets, we're moving into the more specific topics for our conference, which include star and planet interaction. And we have Evgenya Shkolnik from the Lowell Observatory, who's been pioneering this kind of research since her thesis. So, take it away, Evgenya.
Thank you. So thanks very much. Thanks for the reality check this morning. Certainly means we have a lot to learn about exoplanets and what we can actually determine if we were to detect the magnetic fields. And even though, as we learned this morning, it's going to be very hard to really extrapolate a magnetic field detection into true planet properties, it's still worth doing. And hopefully I don't have to convince you all that just having a detection and knowing the different kinds of detections and the frequency of magnetic fields out there is truly valuable, just like just detecting planets and knowing that they're there is also valuable. So I'm going to tell you about detecting extrasolar planetary magnetic fields using star-planet interactions. This is something that we've been doing for over a decade now. And mainly we've been focusing on hot Jupiter systems, and you'll see why in a minute. Okay, maybe not. Hold on. There we go. What's happening to the computer? Anyway, so as we learned this morning, that a detection of magnetic field may or may not be a probe of its internal structure. So for instance, we know that it's metallic hydrogen generating Jupiter's magnetic field. And so the hopes are that if we were to detect an exoplanetary magnetic field, it might imply that there is metallic hydrogen. It might tell us something about the formation mechanism. It also might tell us something about the atmospheric properties and the protection that the magnetic field does provide, especially in a hot Jupiter system that is so close to its parent star. And so this is a similar plot to what Wes had shown, but not including the Kepler candidates. This is just the confirmed exoplanetary systems as of about a year ago. And so we have planetary mass on the y-axis, semi-major axis on the x-axis, and the color coding is the different detection techniques, which I'm not going to get into because those were already covered. But I did want to point out to you where the hot Jupiters actually lie. They typically lie within 0.1 AU, so about maybe 10 or so stellar radii, and they have Jupiter masses, maybe about a third of Jupiter mass and higher. So these are the ones we're going to be talking about. And to give you a real sense of what a hot Jupiter really is, or at least where it really lies, here is an actual image of the solar corona taken during the eclipse. And I've put a fictitious hot Jupiter in there drawn to scale, both in radius and distance. Okay? So this planet is not just close to its star, it's really close to its star. It's actually sweeping through the stellar corona. Okay? And you can imagine that at such distances, some really interesting things are going to be happening to the planet. Atmospheric escape, auroral and radio emission, tidal heating, orbital dynamics, all these things. And you'll be hearing about some of these from Joe in a few minutes. I'm going to talk to you about what the planet is doing to its star. And the reason why is because it's easier to get photons from the star than from the planet. So let's bang away at what we can see. And you can imagine at this distance that there's going to be some sort of magnetic interaction if the planet itself has a strong magnetic field. And there's definitely tidal interaction, and that's observed in a few systems where they have, where the planet and the star are tidally locked, meaning that the orbital period of the planet is the same as the rotation period of the star. So that what that means is that the planet has managed to spin up the star to be locked. And both of these, magnetic and tidal interactions, manifest themselves as increased stellar activity. So that's really our diagnostic, is monitoring stellar activity. This was first proposed by Manfred Kunz and collaborators in 2000, just about the time as I was starting my PhD with Gordon Walker in Vancouver. And what they said was, well, let's take the RS-Canvan model. This actually happens in two solar-type stars that orbit each other very quickly, where the sub-binary point, the hemisphere that's facing each other, actually has a magnetic hotspot that moves along the stellar surface with the rotation, with the orbital period. And so what we're looking for is the period of the activity is equal to the period of the orbit, not just the stellar rotation period, but the period of the orbit. So we can really truly connect it to the planet. And so we've done this actually in a wide range of wavelengths and different atmospheric heights, so probing different heights in the stars. So here's the sun. You guys would recognize it. And you see, this is not an exoplanetary system. And you see the spots. You can measure increased activity in the spots. Or are you laughing at my quote? It's very funny. And then if you move further up from the photosphere and you start probing the chromosphere, right, you can start looking at calcium, H and K, very traditional. You could look at other chromospheric activity indicators in the UV and in the near UV and in other optical indicators. And then you can move your way up, further up into the transition region and into the corona. And there you're looking at X-ray observations, right? And we've done it in all these wavelengths. So ultimately, this is what we're doing, monitoring stellar activity of hot Jupiter hosts, okay? That's the punchline. The very first experiments we did were using high-resolution optical spectroscopy. So this is data taken from the Canada-France-Hawaii telescope on Mauna Kea. Its resolution of this particular one is about 85,000, and the signal-to-noise is very high. We work at signal-to-noise of about 500 per pixel. And that's what you need to do in order to detect tiny, very planet-induced variability. And so the main indicator, chromospheric indicator I'm going to talk about in the next few slides is this calcium H and K lines right here in the blue part of the optical spectrum. But we've also studied H alpha, the helium-1 line, which is a backheated coronal line, and of course there's also calcium infrared triplet. And so what you see here is just the variability. This is now the residuals over time of a calcium 2K line of HD 179949, a hot Jupiter host. And what you see is very clearly the photospheric lines stay rock stable, and then you have this whopping signal that you don't have to be a scientist to know there's something real in there, and it's not in the noise. Now then if you integrate all that, integrate each one of those bumps and wiggles, and you plot it as a function of orbital phase, in this case 3.1 days, then you get this nice phase curve that's stable over a few years. And this we considered is the first detection of star-planet interactions. And we know it's magnetic and not tidal, because if it was a tidal heating source, it would have 2 bumps per phase curve. But here it only has 1. And the cartoon that I got some student to make up for me is sort of this. I know, we could go fancier, but anyways, this is it. You have a planet, you have a spot, and that's what we're looking at. And the stellar rotation period in this case is much longer than the rotation period. So we're not just monitoring a spot as the star rotates. We're actually monitoring something that's connected to the planet. So you might be wondering, why doesn't this happen in our solar system, right? Well, one of the explanations would be because Earth and Jupiter here lie in this regime far away from the star, greater than 100 solar radii from our sun, where this alphane Mach number is greater than 1. This Mach number is defined as the ratio of the wind speed to the alphane speed. The alphane speed being the speed of the magnetic wave. And all hot Jupiters tend to lie in this region here. So within 10 stellar radii, the alphane Mach number is less than 1, right? And so the solar or the stellar wind speed is much less than the alphane speed. And so if you have some sort of magnetic interaction, magnetic reconnection events happening, you can have these things fall back onto the star before being blown off into the rest of the solar system. But of course, nothing's really that nice, and so you come back a few years later, and it looks very different, and you can't plot them up against the planet period anymore, but it works very nicely with a rotation period. And then it comes back, and it goes on. It's what I call the on and off switch. And then back in 2012, an independent team managed to see it again. And so we see this actually on several of our stars, where you have a planet period phase, and then these other ones phase with the rotation period. One thing that is consistent is that that variability that phases with the planet's orbit has a much higher amplitude typically than just a star spot being modulated by the star's rotation. So there's also been lots of star-planet interaction observations from space, and here's just a sampling of it. This is looking at the photosphere using the MOST space telescope. And so they see spots that follow the orbital phase and is consistent from year to year. This is also done with the Kuro space telescope. It's also done using photometry of the photosphere. But this time they didn't see the spotting. What they saw was the flux variance phased with a very short period of the planet at 1.74 days for Kuro 2b. And so that might be telling us something about microflaring events that might be happening in this particular system. And the last little snippet of space observations, even though there's been a lot of work going on lately, is this XMM observations that just came out this year by our group, where we looked at XMM observations of 179949, and we didn't see it vary. I mean, it looks kind of crappy, I understand. But we didn't see it vary with the planet period or the stellar rotation period. In fact, the best period that pops out is the beat period, or the synodic period, which you can imagine if you have, this is now, remember, this is X-rays, so you're now probing up in the corona, and so you might be having some effect where you have, spirals on the star, and the planet is like sweeping through them, and you have to wait a full synodic period before you see the same kind of reconnection again. And the very first 3D EMHD models came out by Ofer Cohen, where he was able to reproduce, actually, the X-ray observations that we had shown. And so here's the planet, here's the star. And he was able to get the power. He was able to measure the power and the phase and get it to work such that you have more closed field lines, and therefore a stronger emission. But what he doesn't have is the stellar field, so he had to use one of the solar reconstructions here. But what we've learned over time is that you really need to understand the star, and that's really what's going on with this on and off business, right? First we see it with some planet-induced activity because it correlates with the planet's orbit, and then we see it, just normal star activity. So what's really happening? And so here's a model by Steve Cranmer and Steve Saar where they show the calcium-2 emission. This is a number of orbits, orbit 0, 1, 2, 3, 4, 5. So 5 consecutive orbits of a fictitious planet implanted 10 stellar radii away from a typical solar magnetic field configuration shows that here's the rotational modulation you would see with a solar rotation, and then here's the enhanced activity induced by the planet. And even from orbit to orbit, you would see it at one, then you wouldn't see it at the other, then you see it at another, then it's a different amplitude, and it's a bit of a mess. So the answer is we really need to understand the star. And as I think the case is with every bit of characterization of any exoplanet, is you need to understand the star. And so Lanza summarizes this equation here, that the power emitted in star-planet interactions is proportional to the magnetic field of the star to the 4/3 power, the magnetic field of the planet to the 2/3 power, and the relative velocity between the two. Right? So or relative velocity, at least between the magnetic field of the star and the planet's motion, right? The planet has to actually be sweeping through the field. If the planet and the star are tidally locked, as I explained earlier, then you have very little relative velocity, right? And you would expect depleted star-planet interactions. And here's an extreme example that came out in the literature by Brendan Miller. And he showed, I'm sure he was originally interested in this because it was an extreme system from the planet's perspective. So you have the planet here at 10 Jupiter masses, right? And an orbital period of 0.94 days. I mean, just envision like what in the world that looks like as a system, and yet he saw no activity. It was dead flat in the variability of the calcium H and K. But if you look at it, the calcium reversals on the inside, the star is dead flat. This actually, WASP-18, is the least active of all exoplanet hosts ever known. Okay, so this is, I think, part of that understanding that no matter how strong your planetary field is, if your stellar field is so weak that you might not be able to detect the star-planet interaction. So in order to start mapping magnetic fields on stars, because we realized this was something we needed to do in order to extract planetary field strengths, we went to a technique called Zeeman Doppler imaging. It's analogous to Doppler imaging, like you would see a spot move through a stellar absorption feature, except you now do it in Stokes V in circular polarization. And you can then map this feature as it passes across a stellar absorption feature. And we use Espedon's, which is spectropolarimeter at CFHT, to do this. And as you'll see, so here's a radial field. As it sticks out, it produces this kind of profile in Stokes V. And an azimuthal field produces slightly different. Did you see that? How it flips, how it's different. So you can not only map the star, the global field strength, but you can actually look at magnetic spots move around. And so what we do then is we take a bunch of those field measurements over a full rotation, and we make these little maps. This is work done by Claire Mathieu and Rim Fares and lots of other people, Jean-François Donati and Moira Jardine, and so on. And so we make a map like this, where this is a projected, it's a flattened projection of the star. So you're looking down at the pole. The bold line here is the equator, and you can start looking at the actual spots, magnetic spots on the star. And then Moira Jardine has this nice code that takes that and makes this an actual representation, a 3D representation of what the stellar field looks like. And then what we can do is do similar things to what Ofer Cohen does and other people, is to then implant a fictitious planet into this magnetosphere and look at what exactly the interaction is, what are the energies, what are the phasing. And we've done this for, I think, maybe 14 stars already. It's hard because you need really high signal to noise, so you can only use the brightest systems to do this. But one of the things that comes out from monitoring stars, as we all know, the longer you look at something, you're going to find something interesting. And that is, we've seen a polarity reversal on Tau Bu. Tau Bu is this short period hot Jupiter system where the planet and the star are tidally locked to each other. And we see this flip, and actually there's more data here where we see the flip again in 2010. So you see the polarity reversal. So someone was earlier talking about magnetic field reversals on our sun having a period of 22 years. Well, in Tau Bu's case, it appears to be 2 years. Okay, this is an F6 star for those of you who are interested. So, so the very original correlation that we saw here, and I'm now working on doubling up the sample, is to test if we're really probing planetary magnetic fields. So here I've plotted the first 13 hot Jupiter systems we've observed. And this is night-to-night variability, short-term variability, that appears to be correlated with the planet's orbit, not stellar rotation, and plotted against mass of the planet over the rotation of the planet, where we assume that they're tidally locked, which I think is a reasonable assumption at these distances. And if you look at the magnetized solar system bodies, this quantity is proportional to the magnetic moment. And so we think we really are probing magnetic fields here. And so then, of course, you're asking, why is Tau Bu off this plot? Well, Tau Bu, as I had said earlier, is the only system that is tidally locked, where the planet orbits the star at the same period that the star is rotating, and means that this VREL is very, very slow. There's some differential rotation, so you get a little bit, and so it's not 0, but it's very, very low in this case. But what you can do then, so if you ignore Tau Bu and you fit a line here, you can measure the power in this activity. And just as an example, then you can get relative magnetic field strengths from this kind of correlation, because we know the stellar magnetic field, and we know VREL. We can calculate this, and a couple other things, and then you get, for an example, this is HD 1799949b, and this is here is 1899733b, that the ratio of their magnetic field strength is probably about 7 or something. So we don't really know, and this is what we need radio observations for, which you'll hear about next, to maybe calibrate this correlation, right? So we can only do relative things here, but it would be nice to pin these points down to real numbers. So, So the last point I want to make is how can we use everything that we've learned about magnetic star-planet interactions to inform us about habitable zone rocky planets? And I don't think it's just for the taxpayer. Oh, I'm a taxpayer, so maybe it is. But I'm really interested. So I'm personally really interested in understanding this question of what is it about magnetic fields that can help us constrain planet habitability? Here's a very simplistic picture, but if we do find a super-Earth or an Earth-like planet with a magnetic field, right, not only will it, hopefully, maybe not, I learned this morning, not at all constrain the interior structure, but maybe constrain the interior structure, but it will also say something about the protection that the magnetic field provides to an atmosphere that we know is needed. So here's the canonical picture of the habitable zone where this swath represents where liquid water could exist. So here's the sun at one solar mass, and you go down to M dwarfs. And you see how it gets closer because M dwarfs are getting cooler, they're lower mass stars. But a few things to point out. One is, here in our solar system, we have several bodies that are within the habitable zone, right? Including the moon. And yet, only one is currently habitable, right? So by definition, just being in the canonical habitable zone where liquid water may or may not exist is very far from the whole picture, right? It's only one piece of the puzzle. We need the magnetic field, we need the plate tectonics, we need a few other things. And so I'd like to take star-planet interaction, into a direction that would help us understand magnetic fields and habitable zone planets. So if this is what I would define as the star-planet interaction zone at 0.1 AU and less, as you get to lower and lower mass stars, we're now starting to probe the habitable zones of M dwarfs. And in fact, there are 6 now reported super-Earths in habitable zone around M dwarfs. So there's really motivation to understand if these are them. And they're all within 0.2 astronomical units of their host star. And so if there is an Earth-like planet with a magnetic field, I hope one day to be detecting them via this technique, or better ways. If by the end of the week, we'll have even better ways to do it, even fabulous, even better. So in conclusion, magnetic star-planet interactions are observable, and hopefully they'll tell us something about the exoplanets that we're looking at. Thank you.